we shall put two values here. First of all, they have not told us which type of body is this. If I knew it's disk or cylinder, I could find out the value of ICM by the familiar formulas. But in this case, we have been just given that mass of the body is capital M and the gyration radius is small k. And so recalling definition of gyration radius, we might write down that moment of inertia of the body about an axis to the center of mass is given by the product of its mass and square of radius of gyration measured about that same axis only to the center of mass. So ICM is equal to m into k square, right? And since they have mentioned that the body rolls down without slipping, the non-slip condition for acceleration is the angular acceleration alpha into the radius of the body must be equal to the center of mass linear acceleration. And therefore, we might write down alpha is equal to center of mass acceleration divided by radius of the body when the body is not slipping during rolling. So putting these two substitutions, ICM is equal to mk square and alpha is equal to ACM by r in equation number 2, we can write down that frictional force Fs into r is coming out to be m into k square, that is ICM. Alpha is equal to ACM divided by r, isn't it? And this is giving me, as you can check, static frictional force is coming out to be m into ACM into k square by r square. Let's look at it once again. We have got frictional force acting at the bottom of this body is equal to product of its mass into acceleration of center of mass ACM into the ratio of the squares of radius of gyration and the actual radius of this round body. So this is my equation number 3, and once we express this Fs in terms of these given quantities, let us put the value of Fs back in equation number 1 and get from here the acceleration of center of mass. So we're going to combine equation number 1 and 3 now and write down that mg sine theta minus Fs, that is m into ACM into k square by r square, this is equal to m into ACM. Now bringing the terms containing ACM on one side, we might write down this is giving us m into ACM inside bracket 1 plus k square by r square is equal to m into g into sine theta. From both sides, the mass of this body m cancels out and we get ACM is coming out to be g sine theta divided by 1 plus k square by r square. So this is the first part of the question, which shows that the acceleration of center of mass of the rolling body is given by free fall acceleration into sine of the angle of inclination of the inclined plane divided by 1 plus gyration radius squared by radius of the body squared. Once we get the value of ACM, we can also find out the static frictional force acting on the body at the bottom from equation number 3. So putting this last result in equation number 3, we might write down static frictional force Fs is equal to m into ACM into k square divided by r square. That is m into, let's put the value of ACM, that is g sine theta divided by 1 plus k square by r square into outside again k square by r square. Dividing both numerator and denominator by k square by r square, we get, you can check it yourself, coming out to be mg sine theta divided by 1 plus r square by k square. So here are the two answers of the first part of the question: acceleration of center of mass of the body and the frictional force acting on the body. Remember, this is static frictional force, but not necessarily the force of limiting friction. So you can't write Fs is equal to mu s into n. You can't write that. This problem 1 has got also a second part, that is part B, and that says that, let me write it here as well. This angle is theta, and if the body were a uniform disk and theta is equal to 30 degree, what would be its acceleration and frictional force encountered? So we already have seen in the first part of the problem that acceleration of center of mass is pointing downwards along this inclined plane, and its magnitude is given by g into sine theta divided by 1 plus k square by r square, where k is the radius of gyration of this round body about this axis through the center of mass. We also found out that the frictional force encountered, this is Fs here, this frictional force is given by m into g into sine theta divided by 1 plus r square by k square. Now, in part before the special case of a uniform disk, the moment of inertia about an axis to the center of mass ICM is given by half into mass of the body into square of its radius. But we also know moment of inertia can be expressed to be the product of the mass and the square of radius of gyration taken about the same axis to the center of mass. So by comparing these two equations, m cancels out and we are getting that gyration radius, that is k squared, is equal to half square of the radius of the disk. We shall make use of this in these previous equations, as well as they have mentioned the value of theta, the angle of inclination of the inclined plane on which this round body is rolling, that is 30 degree. So let us put these two values, and using the first equation, center of mass acceleration ACM is coming out to be g into sine theta is 30 degree divided by 1 plus k square by r square. Now k square is equal to half r square for a uniform disk divided by r square cancelling out. We have got g into sine 30 degree is half. In the denominator we have got 1 plus half, that is giving us 3 by 2 in denominator, and as you can see this is coming out to be g by 3. So we conclude that if this round body is a rigid uniform disk, its center of mass acceleration down the incline is given by 1/3 of the free fall acceleration, provided the theta is also given to be 30 degree. Similarly, going for the frictional force acting on this body up the inclined, that is Fs, given by this formula, right? And we shall put the values now. mg into sine theta is 30 degree divided by 1 plus r square by k square. Now k square for a uniform disk is half r square. So it is r square by half r square. And once again r square cancelling out, we have got mg into sine 30 is half divided by 1 plus 1 upon half, that is 1 plus 2 is coming out to be 3 in denominator, and this is mg upon 6. So we have got the answers for this part B as well. Acceleration is g upon 3 down the incline, and the frictional force acting at the bottom up the incline is static in nature, having a magnitude of the force of gravity on the disk divided by 6. So here are the answers of part B of the question.
Hello students, you got a glimpse of our video lessons through this small lecture. We have hundreds of lectures like this one covering various topics of advanced school level and intermediate physics in our website. They are exhaustive and often accompanied by elaborate diagrams to make concepts even clearer. They are taught with passion and sometimes with a bit of fun. So at the end of the lesson, you have a commanding grip on the subject and you are ready for the board and competitive exams. Subscribe at physicsacademyonline.com to access video lectures of highest standard on various topics of physics.